A supermassive black hole anchors our entire galaxy in darkness. This single object, named Sagittarius, a star, is the heart of the Milky Way, but its true purpose may be far grander. I want to show you how the chaotic core of our home galaxy, a place of unimaginable forces and ancient violence, acts as a unique master key. By the end, you will understand the universal blueprint for how all galaxies are born, live, and die. We will see how echoes of a past cataclysm and stars orbiting at impossible speeds are rewriting cosmic history. What does the quiet power at our galaxy's center reveal about the entire universe? At the very center of this metropolis sits its silent governor, Sagittarius, a star. This supermassive black hole is not a voracious devourer in this moment, but a quiet anchor of immense gravity, its influence stretching across light years. Surrounding it is a nuclear star cluster, a sphere of ancient stars packed so tightly that their average separation is a mere fraction of a light year. In our galactic suburbs, stars are separated by vast emptiness, but here they are neighbors in a crowded city square. This density creates a frenetic environment where close gravitational encounters can slingshot stars into new orbits or even lead to direct collisions over cosmic timescales. Swirling through this stellar crowd are vast, dark clouds of molecular gas and dust, the raw material for new stars. These clouds are not serene. They are churned and compressed by the titanic gravitational tides from the black hole and the jostling stars. Finally, weaving through it all are powerful magnetic fields, invisible threads that can channel particles and shape the flow of matter, adding another layer of complexity to the core's chaotic physics. This entire ecosystem bathes in intense radiation from young, hot stars and from matter heated as it spirals toward the black hole. It is a place of perpetual construction and demolition, where stars are born in frantic nurseries and others are torn apart by gravitational forces. This intricate ballet is not unique. The core of the Milky Way offers us a front-row seat to a spectacle that is likely playing out in the hearts of countless other spiral galaxies. By learning the steps of this dance here in our own cosmic backyard, we are essentially learning a universal language, one that speaks to the fundamental processes governing galactic life everywhere. This unparalleled view is a gift of our cosmic address. We are embedded within the Milky Way, giving us a front-row seat to its chaotic heart that no external observer of another galaxy could ever have. Yet for centuries, that core was hidden behind thick curtains of interstellar dust, completely invisible to traditional optical telescopes. The breakthrough came not with bigger lenses, but with new eyes. Astronomers learned to see in different kinds of light. Infrared telescopes like the pioneering 2-micron all-sky survey and later the Spitzer Space Telescope could peer through the dust, revealing the brilliant tapestry of stars crowded around the center. Radio telescopes such as the Very Large Array mapped the frenetic motion of gas clouds and detected the faint whispers of material spiraling toward the black hole. Then came the crowning achievement, the Event Horizon Telescope. This was not a single dish, but a planet-sized virtual observatory linking radio telescopes across the globe. Its first iconic image, released in 2022, was not of our own black hole, but of the one at the heart of the galaxy Messier 87. That image was a proof of concept, a demonstration that such a feat was possible. The real prize, the image of our own Sagittarius, a star, followed, providing humanity with its first direct visual evidence of the gravitational monster at our galaxy's center. This combination of technologies gives us data of incredible precision. We are not just seeing a blurry smudge of light, we are tracking individual stars like the famous star S2, as they make their frantic, looping orbits around the black hole at speeds exceeding 15 million miles per hour. We measure the wobble of gas clouds, map the structure of magnetic fields, and watch the flickering glow of the black hole's immediate surroundings. For a distant galaxy, even a magnificent spiral like Andromeda, the core is a single, unresolved point of light. All that intricate detail is lost, but here, in our own home, we have a high-definition, three-dimensional model of a galactic nucleus in action. This transforms the Milky Way's core from a mere subject of study into something far more valuable, a detailed reference manual. It is the Rosetta Stone for galactic cores. By understanding the physics, the relationships, and the cause and effect here with such intimate detail, we possess the master key to deciphering the faint, blurred signals we receive from the hearts of galaxies millions or billions of light years away. Every flicker, every strange spectral signature from a distant quasar or active galaxy can now be compared against the known, close-up processes happening right here. Our unique location is not just a convenience, it is the foundational pillar for understanding how all galaxies work at their deepest level. The profound quiet of our galactic center holds its own startling message. Sagittarius, a star, is a sleeping giant, a supermassive black hole on a strict diet. Unlike the brilliant, ravenous quasars seen blazing in distant galaxies, which can outshine every star in their host galaxy combined, our own central black hole is remarkably subdued. It emits only a faint, flickering glow, the equivalent of a candle next to a supernova. This calm is not a sign of weakness, but a profound clue. It tells us that black holes, and by extension the galaxies they anchor, live through distinct chapters. Most of a supermassive black hole's existence is spent in this dormant, quiescent state, like Sagittarius, a star, is now. It is not actively consuming large amounts of gas and dust. But this piece is punctuated by brief, violent eras of feasting. Astrophysicists monitoring our black hole have witnessed these moments. Occasionally, Sagittarius, a star, will flare up, its brightness increasing by orders of magnitude in a matter of hours. These are not full-blown quasar eruptions, but more like small snacks, offering a miniature glimpse into the mechanics of activation. By studying these flares and the overall quiet, scientists can calibrate their models of what are called active galactic nuclei, or a GN. Think of it like this: if a quasar is a volcanic eruption, then Sagittarius, a star, is the dormant volcano we have seismometers on, feeling its occasional rumbles and learning exactly how the magma chamber below functions. This cycle of feast and famine is not just about the black hole, it is the central engine of galactic evolution. When a black hole enters its active phase, the energy it releases is so titanic that it can blow gas and dust clear across the galaxy, halting the birth of new stars and fundamentally reshaping the galactic structure. This feedback mechanism is thought to be why we do not see overly massive galaxies. The black hole literally regulates its own growth and that of its home. Understanding this quiet phase here in our own galaxy gives us the baseline. It tells us what normal looks like. When we look across the universe and see a brilliant quasar, we now understand we are catching that distant galaxy in a rare, transformative moment of crisis and change. The calm of our own giant is the silent key to hearing the distant echoes of cosmic violence everywhere. These ancient stars are more than just points of light, they are living archives. Each one of them, especially the so-called S-stars whipping around the black hole at incredible speeds, carries a record written in its motion, its age, and its very chemical composition. This field is known as stellar archaeology, and it allows us to read the biography of our galaxy page by page. The most direct evidence comes from their orbits. By meticulously tracking stars like S2 over decades, astronomers have mapped their precise elliptical paths around Sagittarius, a star. These are not simple, clean circles. They are rosette-shaped patterns that subtly shift over time. This shift, called precession, is a direct test of Einstein's theory of general relativity in an extreme gravitational environment. But beyond proving relativity, the orbits themselves tell a story of stability and chaos. The fact that these stars exist in such a crowded, violent region at all is a puzzle. According to classical models, the black hole's tidal forces should have torn apart any molecular cloud trying to form stars so close. So how did these stars get there? One compelling theory is that they were not born in place, but were violently delivered. The orbits of some S-stars are highly inclined and eccentric, suggesting they may have been hurled into their current paths during a close encounter with another star or a massive object in the distant past. Some could even be the remnants of a disrupted star cluster that wandered too close to the black hole, its members scattered like cosmic billiard balls. This points to a dynamic, even violent, history in the core, shaped by gravitational interactions over billions of years. The chemical fingerprints of these stars add another layer to the narrative. A star's atmosphere contains the elemental signatures of the cloud from which it was born. Stars in the nuclear cluster are remarkably metal-rich, meaning they contain significant amounts of elements heavier than hydrogen and helium, forged in the hearts of previous generations of stars. This tells us the core has been a site of multiple, intense episodes of star formation and death, recycling material over and over in a cosmic crucible. Perhaps the most profound archaeological find, however, is the population of stars that should not be there at all. Observations have revealed a surprising number of young, massive stars terrifyingly close to the black hole, stars that seem far too young to have migrated in from a safer distance. Their presence suggests a near impossible feat, star birth in the most hostile neighborhood imaginable. The leading explanation is that the black hole itself, through its immense gravity, can compress passing gas clouds enough to trigger a frantic burst of star formation right on its doorstep. This single insight transforms our view of the black hole from a purely destructive force into a paradoxical creator, capable of forging new suns in the shadow of its event horizon. By reading this stellar history book, we are piecing together a timeline. We see evidence of ancient mergers with smaller galaxies whose stars were absorbed into the core. We see records of periodic bursts of frantic star formation, likely triggered by the black hole's gravitational influence on incoming gas clouds. Each star is a data point in a grand simulation of galactic evolution. The story written in their light is not unique to the Milky Way, it is a template. By reconstructing our own galaxies passed from these stellar fossils, we develop the forensic tools to interpret the faint, integrated light from the cores of distant galaxies. We learn the universal signatures of growth by merger, of quiet periods, and of violent awakenings. The orbits of a handful of stars here become the master key to unlocking the life story of every large galaxy in the cosmos. But the quiet giant was not always so still. Extending 25,000 light-years above and below the galactic plane, like two colossal ghosts haunting the Milky Way, are the Fermi bubbles. These are not structures of gas and dust you could see with an optical telescope. They are immense volumes of space filled with high-energy gamma rays and X-rays, discovered only in 2010 by the Fermi Gamma Ray Space Telescope. They are a fossilized scream from the galaxy's heart, the lingering echo of a past cataclysm. The leading theory is that several million years ago, our quiet Sagittarius, a star, awoke in a violent episode of feeding. Perhaps a massive cloud of gas or even a small galaxy ventured too close and was torn apart. As this enormous amount of matter spiraled into the black hole, it did not go quietly. A fraction of the material, instead of crossing the event horizon, was channeled by powerful magnetic fields and blasted outward in two opposing jets, traveling at nearly the speed of light. These jets punched through the dense gas of the galactic disk and inflated these gigantic, energetic bubbles into the halo of hot gas that surrounds our galaxy. The eruption would have been a brief event on cosmic timescales, perhaps lasting only 10,000 to 100,000 years, but its impact was permanent. It sculpted the very environment of our galactic neighborhood. This event demonstrates the core's astonishing ability to influence the entire galaxy, not just its immediate vicinity. The energy injected by those jets heated the galactic halo, the vast, diffuse reservoir of gas that envelops the Milky Way. By heating this gas, the outburst made it harder for the halo to cool, collapse, and form new stars, effectively putting a brake on the galaxy's growth. This process is what astronomers call feedback, a self-regulating mechanism that is now considered fundamental to galaxy evolution. It is a cosmic balancing act. A black hole feeds, grows, and releases a titanic burst of energy. That energy then heats or expels the surrounding gas, starving the black hole of its future fuel and quenching star formation across vast regions. The galaxy and its central engine are locked in a delicate dance, each controlling the other's fate. The Fermi bubbles are our local, tangible evidence of this universal process. By studying their size, their shape, and the energy still trapped within them, we are reading the after-action report of a galactic-scale event. We can measure the power of the ancient jets, estimate how much fuel the black hole consumed, and model how that energy propagated through the galactic ecosystem. This turns a theoretical concept into observable reality. When we look at distant galaxies with similar giant radio lobes or energetic halos, we are not just seeing abstract shapes, we are seeing other Fermi bubbles in different stages of their lives. Our galaxy's ancient eruption provides the master key to understanding how all supermassive black holes, during their brief active phases, become the architects of their galaxies, shaping their structure and destiny with bursts of unimaginable power. This ancient echo of violence is not the only relic shaping our galaxy's story. Encircling the galactic core, within a region spanning roughly 1,500 light-years, lies a cosmic pressure cooker known as the Central Molecular Zone. It is a place of staggering extremes, a dense, churning whirlpool of gas and dust that contains a significant fraction of the entire Milky Way's raw star-forming material. The conditions here are unlike anything found in our quiet galactic suburbs. The gas clouds are crushed under pressures thousands of times greater than elsewhere, sculpted by fierce radiation from the central cluster and whipped into a frenzy by the black hole's gravitational tides. Within this maelstrom, the very rules of star formation are rewritten. In our local spiral arm, stars typically form in relative isolation or in small, loose groups from a single collapsing cloud. Here, in the Central Molecular Zone, star birth is a frantic collective event. Dense clumps within the giant clouds collapse not into single stars, but into entire, glittering clusters, each one containing thousands of stellar newborns packed into a space just a few light-years across. It is a stellar metropolis being built all at once. This environment favors the creation of monsters. The intense pressure and abundant material lead to the rapid formation of exceptionally massive stars, behemoths dozens of times heavier than our Sun. These stars burn with a ferocious blue-white intensity, living fast and dying young in spectacular supernova explosions after only a few million years. Such massive stars are rare in our neighborhood, but in the Central Molecular Zone they are common. This challenges our standard textbooks on stellar nurseries, forcing astronomers to ask how gravity can overcome the incredible turbulence and heat that should, in theory, tear a cloud apart before it can collapse. The answer seems to lie in the very violence of the region. The constant churning and compression from the black hole's influence and frequent supernova might actually trigger collapse by smashing clouds together, creating pockets of such incredible density that they cannot help but form stars. Studying this zone is like finding a living fossil. the chaotic, cluster-forming, massive star-dominated environment of the central molecular zone is a mirror held up to the early universe. Billions of years ago, when galaxies were first assembling themselves from primordial gas, conditions were universally more dense, more turbulent, and more extreme. The first generations of stars, known as population 3 stars, are thought to have been almost exclusively these kinds of massive giants, born in similar frantic bursts. We cannot travel back in time to witness the cosmos in its fiery youth, but we can look toward our own galaxy's heart. The central molecular zone is a local laboratory, a time capsule preserving the physical processes that once governed the entire universe. By decoding how stars are forged in this modern-day crucible, we gain the master key to understanding the dawn of light in the cosmos, and how those first, brilliant stars seeded the universe with the heavy elements that would one day make planets and life possible. Even the most extreme stellar nurseries cannot explain everything at the galactic center. Among the whirling stars and churning gas clouds, astronomers have spotted something truly bizarre, objects that defy simple classification. They are called G objects, and they look like one thing but behave like another. To our telescopes, they appear as faint, extended blobs of gas and dust, similar to the molecular clouds drifting through space. But their motion tells a different story entirely. These G objects are not drifting, they are racing on tight, elongated orbits around Sagittarius, a star, moving with the speed and precision of stars. It is as if you saw a cloud in the sky, but then watched it suddenly dart across the heavens like a fighter jet. This contradiction makes them a profound mystery. How can a diffuse cloud of gas hold itself together under the black hole's immense gravitational tides, forces that should shred it apart in a single orbit? The leading theory is as fascinating as the objects themselves. Scientists now suspect G objects are not clouds at all, but stars in disguise. The chaotic core of our galaxy, with its incredibly crowded stellar dance floor, creates opportunities for extremely close encounters. The idea is that binary star systems, 2 stars orbiting each other, can be driven to merge by the black hole's gravitational nudges over millions of years. When 2 stars spiral together and coalesce, the colossal energy of that merger blows off an enormous shroud of gas and dust. This expanding cloak obscures the merged star at the center, making it look for centuries like a simple, puffy cloud. But inside, the combined stellar object continues on its orbit, a hidden heavyweight following the laws of stellar motion. We may be witnessing the slow, cosmic aftermath of stellar collisions. The study of these strange entities is a direct test of our understanding of physics in the most crowded neighborhoods of the universe. Processes like stellar mergers are almost certainly happening in the dense cores of other spiral galaxies, but from millions of light-years away, we would never see the faint, dusty aftermath. Only here in our own galactic nucleus can we track these individual G objects, watch their orbits change, and monitor how their dusty shrouds evolve over time. Their very existence challenges our neat categories. They force us to ask what truly defines a star, a cloud, or a single object. Each G object is a reminder that the galactic center is a laboratory of radical transformation, where the familiar rules of astronomy are bent and rewritten by sheer gravitational force. By decoding their nature, we gain another crucial piece of the puzzle, a key to understanding the hidden, violent relationships that shape the hearts of galaxies everywhere. Beyond the light and the radio whispers, the core hums with a deeper, more fundamental music. It is a symphony written not in photons, but in the very fabric of spacetime itself, a continuous vibration generated by the sheer density of dead and dying stars. Orbiting the supermassive black hole are not just ordinary suns, but the incredible remnants of stellar lives, compact objects of almost unimaginable density. White dwarfs, the Earth-sized cores of expired stars, Neutron stars, city-sized spheres where a sun's worth of mass is crushed into a single sugar cube of matter. And stellar mass black holes, the dark shadows of massive stars that ended their lives in collapse. In that crowded stellar city square, these objects are constantly dancing around each other, their immense masses creating ripples in space-time as they move. Each individual ripple is too faint for our current detectors to hear, but together they should create a persistent, low-frequency hum, a gravitational wave background noise emanating from the heart of our galaxy. Think of it like standing in a vast stadium. You cannot make out the individual conversations of thousands of people, but you hear the steady, collective roar of the crowd. That roar is what future observatories are being built to listen for. Projects like the Laser Interferometer Space Antenna, or LISA, a planned fleet of 3 spacecraft flying in a giant triangle millions of kilometers apart, are designed specifically to tune into this low-frequency gravitational universe. Detecting this hum would be a revolution in how we see the galactic core. Light can be blocked by dust, and even X-rays only show us the most energetic events. But gravitational waves pass through everything unimpeded. They would offer a direct census of the invisible population, allowing us to count the hidden stellar black holes and neutron stars that optical telescopes could never find. We could map their distribution and understand their dynamics purely through the ripples they create in the cosmos. This is the promise of multi-messenger astronomy, combining the old language of light with the new language of space-time vibrations. By learning to interpret this silent symphony from our own galactic center, we will possess the ultimate master key. We will have a new, universal tool for probing the densest regions of all galaxies. The faint, collective hum we hope to hear from Sagittarius, a star, will be the same frequency we can search for in the cores of distant, fuzzy spirals. It will tell us not just what those cores look like, but what they weigh, how their hidden masses are moving, and how many dark remnants are hiding in their bustling stellar crowds. The core's deepest secrets are not written in light, but in the quiet, rhythmic stretching of the universe itself. The silent symphony of gravity is not the only fundamental force at play in the core. There is also a storm of pure energy, a relentless bombardment of particles traveling at nearly the speed of light. These are cosmic rays, and their origin has been one of astronomy's longest-standing mysteries. The galactic center is now revealing itself as one of the universe's most powerful natural particle accelerators, a cosmic version of facilities like the Large Hadron Collider, but operating on a scale we could never hope to build. The immense power source for this accelerator is the supermassive black hole itself, or more precisely, the chaotic environment it commands. When vast clouds of gas are shredded by the black hole's gravity, or when shock waves from ancient supernova blast through the dense medium of the central molecular zone, they create violent, turbulent regions. Within these maelstroms, tangled magnetic fields of incredible strength act like vast, invisible racetracks. Charged particles like protons and electrons become trapped in these fields, whipping back and forth. With each pass through a shockwave, they gain a little more speed, a little more energy, in a process called Fermi acceleration. Over time, some of these particles are boosted to energies billions of times greater than anything produced in our most powerful machines on Earth, and then flung out into the galaxy. We cannot see these particles directly as they streak through space, but we can see the brilliant signatures they leave behind. When an ultra-high energy cosmic ray collides with a stray atom of gas or a photon of light, it can generate a flash of gamma rays, the most energetic form of light in the universe. Space telescopes like Fermi and the Chandra X-ray Observatory have mapped a bright, diffuse glow of gamma rays and X-rays emanating from the central 100 light-years of our galaxy. This glow is not coming from stars or the black hole's faint emission. It is the telltale sign of this relentless particle bombardment, a constant hail of invisible bullets striking the interstellar medium and announcing their presence with pinpricks of extreme light. By carefully analyzing this high-energy glow, scientists can reverse engineer the accelerator. The map of gamma rays acts like a blueprint, revealing where the magnetic fields are strongest, where the shock waves are most powerful, and how efficiently the core is turning gravitational and explosive energy into a flood of relativistic particles. This transforms our galactic center from a mere object of study into a foundational reference. The physical processes we decipher here, the intricate dance between turbulence, magnetic fields, and particle acceleration, are almost certainly universal. When we look at the distant, brilliant jets erupting from active galaxies, or the faint but immense radio lobes surrounding galaxy clusters, we are seeing the same physics operating on a gargantuan scale. The faint gamma-ray glow from Sagittarius, a star's neighborhood, is a scaled-down model of the most energetic phenomena in the cosmos. Understanding how our local, quieter accelerator works provides the master key to unlocking the power source for events that shape the evolution of entire clusters of galaxies, events whose energies defy human comprehension. The heart of our Milky Way is not just a place of stars and gravity. It is a factory for the fundamental particles that constantly rain down on our world, and its blueprints are written in light of the highest energy. But the chaos of the core is not lawless. It is channeled by an invisible architecture. Woven through the churning gas and the frantic stellar orbits is a network of powerful, organized magnetic fields. These are not the weak, scattered fields of our galactic suburbs, but a pervasive and forceful presence, a kind of cosmic skeleton that gives shape to the entire inner galaxy. Imagine the difference between the random iron filings scattered on a table and the elegant, looping lines that form when you place a magnet beneath. In the galactic center, the magnet is the combined gravity and motion of the entire region, and the filings are the ionized gas and cosmic rays, aligning to reveal a hidden framework. These fields are extraordinarily strong, thousands of times more powerful than Earth's magnetic field, and they act as guiding rails for the interstellar material. Vast clouds of molecular gas do not simply fall haphazardly toward the black hole. They slide along these invisible filaments, their motion choreographed by magnetic pressure as much as by gravity. This magnetic guidance system is crucial for regulating the black hole's diet. The process of accretion, how a black hole feeds, is not a simple gravitational gulping. For matter to lose enough energy to spiral inward, it must shed its angular momentum, and magnetic fields provide the essential friction. They tangle and connect the infalling gas, creating a kind of magnetic viscosity that allows the material to slow down and drift closer to the event horizon. Without this magnetic skeleton, matter might simply orbit forever in a vast, ineffective disk, and the black hole would starve. These fields also play a paradoxical role in star formation. Within the central molecular zone, the intense magnetic pressure can actually support giant gas clouds against their own gravity, preventing collapse and putting a brake on the birth of new stars. Yet, in other areas, the fields can become so concentrated that they themselves trigger collapse by crushing clouds along specific axes. This dual nature makes magnetic fields the great moderators of the core, both an inhibiting force and a creative one. Cutting-edge research using instruments like the Stratospheric Observatory for Infrared Astronomy, SOFIA, and the Atacama Large Millimeter Array, ALMA, is now mapping these fields in unprecedented detail by measuring the subtle polarization of light emitted by dust grains aligned with the magnetic lines. The maps reveal stunningly ordered structures, vast magnetic filaments stretching for dozens of light years, some pointing directly toward Sagittarius, a star like cosmic road signs. These filaments are the physical manifestation of the core's hidden skeleton. Since magnetic fields are a universal component of all galaxies, deciphering their complex, dynamic role in our own core is a foundational step. Every simulation of galaxy evolution that ignores this magnetic architecture is building a model of a ghost, a body without a skeleton. By learning how these invisible lines of force guide, shape, and regulate the heart of the Milky Way, we gain the master key to understanding the fundamental engineering principles behind the growth and structure of every massive galaxy in the universe. Our galactic center is not an isolated specimen, it is part of a cosmic family. Just 2.5 million light-years away lies the Andromeda galaxy, a grand spiral that is both our twin and our mirror. It is the nearest large galaxy to our own, a close enough neighbor that we can study its core in remarkable detail, allowing for a direct comparative anatomy of two galactic hearts. At first glance, the similarities are profound. Like our Milky Way, Andromeda is anchored by a supermassive black hole, one with a mass estimated to be over 100 million times that of our Sun. It is also surrounded by a dense, ancient nuclear star cluster, a familiar bustling stellar metropolis. This tells us that the basic architectural blueprint for a large spiral galaxy is consistent. A supermassive black hole and a dense stellar hub are universal features. But look closer and the differences become a thrilling source of insight. The most striking distinction is one of activity. While our Sagittarius, a star, is quiet, Andromeda's central black hole is even quieter, almost eerily dormant. It shows virtually no signs of accretion or the flickering flares we see in our own core. This reveals a critical fact: the dormant phase of a black hole's life cycle is not a brief anomaly, but likely the dominant state for most supermassive black holes most of the time. The real intrigue, however, lies in Andromeda's structure. High-resolution images from telescopes like Hubble have revealed that its core is not a single, smooth peak of light. Instead, it possesses a double nucleus, two distinct brightness peaks nestled at its very heart. This is not two black holes, but a fascinating cosmic scar. The leading explanation is that Andromeda's core bears the marks of a dramatic past merger, a collision with a smaller galaxy that occurred billions of years ago. During that event, the smaller galaxy's own central black hole and star cluster were absorbed, but they did not fully settle. The result is this double structure, a fossilized record of a violent act of galactic cannibalism. This comparative analysis between our galaxy and Andromeda is not just academic, it is the foundation of a scientific method on a galactic scale. By placing these two detailed portraits side by side, astronomers can begin to separate the universal from the unique. Is a double nucleus common, or is Andromeda a special case? What does the extreme quiet of both black holes tell us about the typical fuel supply in mature spirals? Our local group of galaxies becomes a controlled laboratory. We have two massive spiral galaxies of similar size and age that have clearly experienced different histories. One, our Milky Way, shows evidence of a past energetic outburst in its Fermi bubbles. The other, Andromeda, shows the structural aftermath of a major merger. By studying both, we start to build a taxonomy of galactic centers, a classification system based on observable features that tell stories of past events. This is how we move from understanding a single heart to comprehending the life cycles of all galaxies. Each core is a biography, and by comparing chapters from two nearby volumes, we learn to read the entire library of the cosmos. The subtle differences between our galaxy and Andromeda provide a critical reality check, but to truly unlock the universal rules, we must build entire galaxies from scratch. Since we cannot run experiments on the cosmos, astrophysicists turn to the most powerful supercomputers on Earth, constructing digital universes governed by pure mathematics. These are not simple animations, they are intricate theoretical frameworks where every particle of gas, every star, and every ripple of gravity is accounted for by billions of lines of code. To simulate the chaotic heart of a galaxy, scientists must feed these digital laboratories with the fundamental laws of physics, gravity, hydrodynamics, the behavior of magnetic fields, and the effects of intense radiation. The goal is breathtakingly ambitious: to start with a virtual cloud of primordial gas and watch it, over billions of simulated years, collapse under its own gravity, swirl into a disk, and form a swirling spiral with a supermassive black hole at its center. The true test comes when they zoom in on that digital core. They can watch how gas clouds spiral toward the virtual black hole, testing theories of accretion, the process of feeding. They can see if and where stars form in the tumultuous environment, and most importantly, they can trigger the black hole to become active and observe how the resulting blast of energy, the feedback, pushes back on the galaxy, shutting down star formation. This creates a dynamic loop of growth and regulation, but a simulation is only an elegant guess until it meets reality. This is where our own galactic center becomes irreplaceable. It acts as the ultimate benchmark, the cosmic Rosetta Stone for these virtual worlds. Researchers will run their most detailed simulations, focusing on a region the size of our galactic core, and then compare the output directly with what we actually observe. Does the simulation produce a population of stars with orbits that match the frantic paths of stars like S2? Does it generate the same strange objects like the G objects, moving as compact masses shrouded in gas? Does the simulated black hole flicker and flare with the same irregular patterns as Sagittarius, a star? When the digital prediction and the telescopic observation align, it is a moment of profound validation. It tells us that the physics coded into the simulation, the complex interplay of forces we believe are at work, is likely correct. That validation is the master key. It gives us the confidence to hit play on those same simulations and point them toward the distant, fuzzy cores of galaxies billions of light years away. We can apply the now-tested models to quasars and active galaxies, using them to reverse engineer events we could never witness in real time. The supercomputer becomes a time machine, and our own galactic center is the calibration point that ensures its journey into the unknown is guided by truth. Yet the supermassive black hole is not the only gravitational power in the core. According to the laws of physics, a hidden population of smaller black holes should be there, drawn in by the immense gravity like iron filings to a magnet. These are the intermediate mass black holes, cosmic middleweights that could solve one of the greatest puzzles in astronomy. How do supermassive black holes grow so incredibly large so quickly? The theory of hierarchical growth suggests that Sagittarius, a star, did not form as a giant. Instead, it likely started as a smaller seed, perhaps a remnant from the collapse of a primordial gas cloud or a large stellar black hole. Over billions of years, it grew by feeding on gas and, crucially, by merging with other black holes that migrated into the core. This process should leave behind a swarm of these intermediate objects, black holes with masses ranging from a few hundred to a few 100,000 times that of our Sun. They are the missing links, the crucial stepping stones between the stellar mass black holes born from dying stars and the supermassive monsters that anchor galaxies. Finding them is not just about completing a cosmic family tree. It is about validating the very story of how galaxies build themselves from the inside out. The hunt for these elusive objects is a detective story playing out in the data from our galactic center. Astronomers search for their subtle fingerprints. One method looks for the telltale flickering of X-rays. If an intermediate mass black hole is quietly accreting gas from a passing cloud or a captured star, the infalling material will heat up and glow in X-ray light before vanishing forever. Telescopes like Chandra have catalogued many faint, variable X-ray sources in the core, some of which could be these hidden middleweights having a small, silent meal. Another clue comes from the motion of the stars themselves. An unseen intermediate mass black hole, orbiting within the dense nuclear cluster, would gravitationally tug on the nearby stars, causing them to jitter or follow slightly perturbed paths. By tracking the orbits of thousands of stars with exquisite precision, astronomers hope to spot the subtle wobble that betrays the presence of a dark, massive companion. Perhaps the most dramatic signature would be the ripple in spacetime itself. When two of these intermediate black holes spiral together and merge, they would release a burst of gravitational waves with a frequency perfect for future space-based observatories like LISA to detect. Finding even a handful of these objects in our galactic core would be a monumental discovery. It would strongly support the hierarchical growth model, painting a picture of our galaxy's heart as a dynamic construction site, where smaller black holes have been merging and building up the central giant over cosmic time. This would also solve a practical mystery of the core's dynamics. The observed motions of the dense star cluster are so rapid and complex that some scientists suggest they require the gravitational influence of an unseen, distributed mass, a sort of dark scaffolding. A population of dozens or hundreds of hidden intermediate mass black holes could provide exactly that invisible structure, acting as gravitational anchors that help shepherd the frantic stellar orbits. If this predicted population is confirmed to be hiding in the heart of the Milky Way, it gives us a powerful universal key. It would strongly suggest that similar swarms of middleweight black holes reside in the cores of all large galaxies, acting as the universal building blocks and hidden architects of their central giants. The quiet core of our own galaxy may hold the missing links to a story of growth that spans the entire cosmos. Even the hidden swarm of black holes cannot match the destructive power of the central giant when a star makes a fatal mistake. The vast majority of stars in the nuclear cluster follow stable, if frantic, orbits, held in a perpetual dance by the black hole's gravity. But in a region of such density and chaos, gravitational nudges can occasionally send a star on a new, disastrous trajectory, one that brings it within the Roche limit of Sagittarius, a star. This is the point of no return where the black hole's tidal forces, the difference in gravity between the star's near side and its far side, overcome the star's own self-gravity. What follows is one of the most violent events in the universe, a tidal disruption event. The star is not swallowed whole. Instead, it is stretched into a long, thin strand of stellar material, a process called spaghettification. This stream of gas then wraps around the black hole, colliding with itself in a furious, luminous accretion disk hotter than 1,000,000 suns. For a brief period, weeks to months, this single demolished star can outshine every other source in the galactic core, blazing across the electromagnetic spectrum from X-rays to radio waves. For astronomers, such an event is not just a spectacle, it is a perfect natural experiment. It is as if the universe itself has designed a laboratory to probe the most extreme physics. The sudden, intense influx of fresh fuel allows scientists to watch the entire process of accretion, how a black hole feeds in real time and from a known starting point. They can measure the black hole's spin by how quickly it drags the surrounding spacetime, and test models of how jets and outflows are launched from the chaotic maelstrom. While these events are rare, perhaps occurring only once every 10,000 to 100,000 years in a galaxy like ours, our position offers an unparalleled opportunity. We are in the perfect place to catch one from the very first flash. Observatories around the world and in space maintain a constant watch on the galactic center, a monitoring campaign that would be impossible for any other galaxy. If a star is torn apart, we will see the light curve rise and fall with exquisite detail, track the composition of the stellar debris, and witness how the black hole's immediate environment responds to the sudden feast. This detailed data would be a Rosetta Stone for interpreting the hundreds of similar flares we have already seen in distant galaxies. Those far-off events appear as single, brilliant points of light, their stories compressed and blurred by millions of light-years of travel. We can measure their total energy and rough timescale, but the intricate physics is lost. A tidal disruption event in our own backyard would provide the high-resolution key to decode all those distant, fuzzy signals. It would tell us exactly what a brilliant flare in a faraway galaxy truly means, transforming it from a mysterious blip into an understood chapter in that galaxy's life. Our quiet core holds the potential for a sudden, brilliant revelation, a stellar demolition that would, for a fleeting moment, illuminate the fundamental workings of gravity and destruction for the entire cosmos to see. The violent destruction of a single star is a fleeting event, but the core's long-term vitality depends on a far slower and grander process. Our Milky Way is not a perfect pinwheel, it is a barred spiral galaxy. At its heart, a dense, elongated structure made of billions of stars rotates like a slow, celestial paddle wheel. This galactic bar is not a static feature, it is a dynamic engine for change, and its influence stretches all the way to the doorstep of the supermassive black hole. The bar's immense gravity acts as a cosmic shepherd. As it rotates, it tugs on the orbits of stars and, more importantly, on the vast reservoirs of gas that drift between them. This gravitational interaction creates what astronomers call orbital resonances, zones where the push and pull of the bar's rotation align with the natural orbital periods of the gas. The effect is to funnel material inward, slowly but relentlessly draining the galaxy's outer disk and channeling fresh fuel toward the core. It is a slow-motion fuel line, delivering the raw material that can eventually feed the black hole and spark new generations of stars in the central molecular zone. This process is the essence of what is known as secular evolution. Unlike the dramatic, collision-driven evolution that can reshape a galaxy in a single violent merger, secular evolution is the story of slow, internal change. It is the gradual transformation of a galaxy from the inside out, driven by its own internal structures like bars and spiral arms. Think of it as the difference between a sudden earthquake that reshapes a landscape overnight and the slow, persistent flow of a river that carves a canyon over millions of years. The galactic bar is that river, and its current flows directly to the center. This slow drip feed of gas has profound implications for the core's activity cycle. It provides a steady, regulated supply of fuel that can maintain the black hole's faint, flickering state for eons. More importantly, it may be the mechanism that triggers the black hole's transition from dormancy to activity. If the inflow rate increases, perhaps due to the bar interacting with a particularly dense gas cloud, the black hole could begin to accrete more rapidly, lighting up in a temporary outburst. After the outburst, the feedback energy blasts outward, possibly shutting off the inflow temporarily, and the slow, secular process begins again. This creates a self-regulating loop where the large-scale structure of the galaxy itself governs the heartbeat of its core. Understanding this connection between the galactic bar and the core gives us a universal template. Bars are common in spiral galaxies, suggesting that this internal fuel delivery system is a standard feature of cosmic architecture. By studying how our own bar channels gas inward, we can interpret the faint signatures of gas flows in distant barred spirals. We can begin to predict which galaxies might be on the verge of activating their central black holes based on the strength and orientation of their bars. The quiet rotation of a billion stars in the galactic bar, a process unfolding over hundreds of millions of years, ultimately holds the key to the intermittent violence at the galaxy's very heart. It is a reminder that to understand the monster in the core, we must first comprehend the slow, majestic dance of the entire galaxy that sustains it. But the visible chaos of stars and gas is only part of the story. There is a deeper, invisible architecture shaping the core, a presence felt only by its ghostly gravitational pull. This is the shadow of dark matter, the universe's most enigmatic substance, and the heart of our galaxy may be the perfect place to finally detect its hidden hand. While the supermassive black hole and the dense nuclear star cluster dominate the center's gravity, their combined mass cannot fully explain all the observed motions. There are subtle, persistent hints in the data, slight anomalies in how stars and gas clouds move, that suggest an additional, unseen mass is woven into the fabric of the core. This missing mass could be a vast, diffuse halo of dark matter, drawn in and concentrated by the immense gravity of Sagittarius, a star over billions of years. If dark matter particles, as some theories suggest, can interact with each other, this dense concentration could become a site of continuous, silent annihilation. When two dark matter particles collide, they could theoretically transform into a flash of gamma rays or other high-energy particles we could detect. Telescopes are now carefully sifting through the gamma-ray glow from the galactic center, searching for an excess, a specific signature that cannot be explained by any known astrophysical process like pulsars or cosmic ray collisions. Finding that signal would be a direct window into the particle nature of dark matter itself. Another approach is even more precise, relying on the exquisite celestial choreography we can observe. By tracking the orbits of stars, especially those farthest from the black hole in the nuclear cluster, astronomers can create a detailed map of the gravitational field. Any deviation from the expected path, after accounting for the pull of every visible star and gas cloud, would be the fingerprint of dark matter's invisible mass. It would be like watching a dancer on a stage and seeing their steps subtly tugged by a hidden partner in the shadows. Deciphering dark matter's role here is more than an academic exercise. It is a fundamental test for its properties across the cosmos. Does dark matter cluster tightly around supermassive black holes, forming a dense spike, or is it smoothly distributed? The answer would tell us how this mysterious substance behaves under the most extreme gravitational conditions, refining our models for everything from the formation of the first galaxies to the fate of the largest galaxy clusters. The core of the Milky Way, with its unique, detailed observability, acts as a natural laboratory for this universal mystery. A detection here would provide the master key to mapping the invisible skeleton that holds the entire universe together. The silent hum of gravity and the storm of cosmic rays are just two channels in a much wider cosmic symphony. We are entering a new era where we will listen to the galactic core with every sense the universe provides. This is the dawn of multi-messenger astronomy, a discipline that moves far beyond the traditional study of light. It combines the ancient language of photons with the faint whispers of ghostly neutrinos, the direct impact of cosmic rays, and the ripples of gravitational waves. Each of these messengers carries a unique piece of the truth, filtered through different physical processes, and only by combining them will we see the core in its complete, multi-dimensional reality. Neutrinos, for instance, are nearly massless particles that interact so weakly with matter they can travel straight through a light year of lead. When a star is torn apart by the black hole, or when particles are accelerated to extreme energies in the core's magnetic maelstrom, they should produce a flood of these ghostly particles. Detectors buried deep underground, like Ice Cube at the South Pole, are waiting to catch just a handful of these neutrinos and trace their paths back to the heart of our galaxy. A single confirmed neutrino from Sagittarius, a star, would be a direct telegram from the site of the most violent acceleration, telling us exactly what is happening right now at the event horizon itself, unobscured by dust or distance. Meanwhile, the future Gravitational Wave Observatory (LISA) will tune its ears to the low-frequency hum from the dense population of white dwarfs, neutron stars, and stellar black holes. That collective vibration will paint a dynamic mass map of the core's invisible architecture. Imagine putting together a puzzle where one messenger gives you the shape of the pieces, another gives you their color, and a third tells you how they are moving. The combined picture is transformative. We will not just see a bright region in an image, we will know its weight, feel its vibrations, and receive particles that travel directly from its most energetic events. Our galactic center is the perfect and only place to develop this integrated toolkit. It is close enough that signals from these different messengers are strong enough to detect and correlate with each other. We can point our neutrino detectors, our gamma-ray telescopes, and our future gravitational wave antennas all at the same known target and ask, what story do they tell together when the black hole flares? When a gas cloud is consumed, this makes the Milky Way's core the ultimate proving ground, a local laboratory where we will debug the multi-messenger models and learn to interpret the combined data stream. The methods and correlations we establish here will become the universal standard. Once refined, we will point this entire suite of sensors at the brilliant, blurred cores of distant active galaxies and quasars. The faint neutrino flux or the specific gravitational wave signature we learn to read from our own quiet giant will become the master key for deciphering the furious physics of those distant monsters. Our home galaxy's heart is not just a subject of study, it is the training ground for the next century of cosmic discovery, teaching us to see the universe in all its invisible dimensions. The galactic core is more than a place of chaos, it is a mechanism of profound cosmic order. To grasp its true purpose, picture it as the mainspring of a galactic clock. In this intricate timepiece, the supermassive black hole is the central gear. Its immense mass and furious spin set the fundamental tempo for everything around it, the relentless tick of gravity that dictates orbital speeds and gravitational tides. The stars whipping around it, from the frantic S-stars to the ancient giants of the nuclear cluster, are the clock's hands. Their precise, predictable motions trace the passage of galactic time, each complete orbit marking a chapter in the core's long history. And the outflowing energy, the Fermi bubbles and the occasional brilliant flare, that is the chime. It is the striking mechanism that marks a major event, a transformative outburst that resets the local environment and echoes across the galaxy. Just as a master clockmaker can understand any timepiece by studying its central mechanism, we can begin to comprehend galaxies across the universe by deciphering the workings of this one local cosmic clock. The steady ticking of stellar orbits tells us about the clock's stability and the weight of its central gear. The rare, resonant chime of an energetic outburst reveals how the clock marks epochs of change. By learning to read this clock, we are not just observing our own neighborhood, we are learning to tell time for the entire cosmos. Every distant galaxy has its own version of this clock, its own central gear and moving hands, but the fundamental principles of the mechanism, the physics of gravity, accretion, and feedback, are universal. Our galactic center is the master timepiece laid open on the workbench, allowing us to see every gear and spring in action, so we can then understand the timekeeping of island universes billions of light years away. For countless generations, that dense patch of stars in the constellation Sagittarius has drawn the human gaze. Long before telescopes, ancient cultures wove its faint, milky glow into their understanding of the world. For some, it was a celestial river, a pathway for spirits, or the very campfire of creation. These were not scientific descriptions, but they shared a profound intuition that the center of the sky held a special organizing power. It was a place of origin, of gods, of ultimate mystery. This human impulse to look toward the center and find meaning is a thread that runs unbroken through time, simply changing its language with each era. The shift from mythology to astronomy began with the simple act of pointing a lens at the night. In the early 20th century, as astronomers mapped the spiral structure of our island universe, they theorized a massive gravitational anchor at its heart. Yet the core itself remained frustratingly hidden behind great walls of interstellar dust. The breakthrough arrived not with light but with static. In the 1930s, a radio engineer named Karl Jansky, investigating sources of interference for Bell Telephone Laboratories, discovered a persistent hiss emanating from the constellation Sagittarius. He had accidentally tuned into the galaxy's heart, picking up the radio waves generated by its frenetic activity. This was the first time humanity perceived the center not as a silent symbol, but as a physical source of energy. The object was named Sagittarius, a star. For decades, it remained an enigmatic radio beacon. Then, in the late 20th century, new technologies like infrared astronomy finally pierced the dust, revealing the stunning spectacle of stars orbiting nothing at all at millions of miles per hour. The only thing that could explain such frantic motion was an object of monstrous density, a gravitational trapdoor in space. The mythical abode of spirits had been translated into the precise language of physics, a supermassive black hole. This historical arc is more than just a timeline of discovery. It is a mirror. Each interpretation of the center, from spiritual home to radio source to gravitational monster, was the best answer our species could provide with the tools and concepts available. Our ancestors saw a divine hearth because that framework gave the universe order and purpose. We see a black hole because our framework is built on mathematics and observational evidence. Yet both perspectives are driven by the same deep-seated curiosity, a need to look toward the luminous heart of our home and ask what power resides there. Our modern quest to use this core as a key to all galaxies is not a departure from this ancient story. It is its latest, most detailed chapter. We are still seeking order from the center, still trying to read the blueprint of the cosmos from its most concentrated point of energy. The telescopes have changed, but the direction of our gaze and the wonder behind it remains profoundly human. This profound stability raises a deeper, almost philosophical question. Could the quiet nature of our galactic core be more than just a scientific curiosity? Could it, in fact, be a silent, non-negotiable requirement for our own existence? This idea connects to a broader concept known as the galactic habitable zone. Just as a planet must orbit within a star's narrow band where liquid water can exist, a solar system may need to reside in a specific region of a galaxy that is just right for life. A critical factor in this galactic real estate is the temperament of the central black hole. Consider the alternative. If Sagittarius, a star, were in a bright, quasar-like phase, as many galactic cores were in the distant past, it would transform from a quiet anchor into a cosmic blowtorch. The intense radiation pouring from the core, from X-rays to gamma rays, would flood the galaxy. This lethal bath of high-energy particles could strip away planetary atmospheres, disrupt the delicate chemistry of forming worlds, and create an environment far too hostile for the slow, gradual evolution of complex molecules necessary for life. Our solar system's position, about 27,000 light-years from the center, might be within a sterilized zone. The very spiral arms that gave birth to our sun could also become lanes of celestial danger. This paints a startling picture of cosmic timing. Our emergence on a pale blue dot coincides with a specific, mature chapter in our galaxy's life. The frantic construction of the early universe has settled. The core has entered a long, stable period of relative calm between violent outbursts. The Fermi bubbles are evidence of a past eruption, but that event happened millions of years before the first hominids walked the Earth, its energy long since dissipated into the galactic halo. We are living in the peaceful aftermath. This invites a powerful reflection. Is the tranquility we observe a mere fortunate accident, a happy coincidence in the vast randomness of the cosmos? Or is it a common, necessary feature for any galaxy that hopes to cradle life? If a violently active core is a galaxy's fiery adolescence, then complex life may only arise during its long, stable adulthood. Our existence, then, may be subtly but inextricably tied to the present state of the galactic heart. The same forces that sculpt stars and dictate the flow of gas also, from an immense distance, write the silent rules for biological possibility. The key to understanding all galaxies might also be the key to understanding our own improbable place among them. Even with all we have learned, the galactic center refuses to surrender all its secrets. For every answer gleaned from its light, a new, more puzzling question seems to emerge. These are not failures of science, but its very fuel, the persistent mysteries that remind us how much we have yet to understand. One of the most glaring puzzles is a profound absence. Given the frenzied history of star formation and death in the core, scientists confidently predicted it should be swarming with the dense, spinning corpses of massive stars known as pulsars. These neutron stars act like cosmic lighthouses, beaming out regular pulses of radio waves that are relatively easy to detect. Yet, despite extensive searches, only a handful have been found where hundreds were expected. This is the missing pulsar problem. Where did they all go? It is possible our models of stellar evolution in such an extreme environment are wrong, and massive stars there die differently, perhaps collapsing directly into black holes without leaving a spinning neutron star behind. Or perhaps the intense magnetic fields or the dense fog of free-floating electrons in the core are scrambling the pulsar signals, making them invisible to our current telescopes. Each missing pulsar is a silent question mark, challenging our assumptions about how stars live and die in the universe's most crowded neighborhoods. Then there are the Fermi bubbles themselves. While the leading theory of a past black hole outburst is compelling, the details remain frustratingly vague. What was the precise trigger for that cataclysmic meal? Was it a single, gigantic gas cloud, or the disrupted core of a small galaxy? How long did the feast last, and what was the exact mechanism that focused the energy into two such clean, symmetrical lobes? Current observations give us the aftermath, the fossilized shape of the explosion, but not the spark that lit the fuse. Unlocking this could tell us not just about our galaxy's past, but about the typical rhythm of these outbursts, helping predict when and how other galaxies might experience similar transformative events. Perhaps the most visually obvious mysteries are written in the orbits of the stars themselves. The frantic paths of the S-stars are now well mapped, but their very existence so close to the black hole remains a paradox. How did they get there? The traditional idea of stars forming peacefully from a gas cloud seems impossible so deep within the black hole's destructive grasp. The stellar merger theory for the strange G objects is elegant, but is it the whole story? Some stars appear suspiciously young for their dangerous location, suggesting they were born in place against all odds. This implies our black hole can be a creator as well as a destroyer. But the physics of triggering star birth in a maelstrom of tidal forces is a puzzle we are only beginning to piece together. Each anomalous orbit is a clue to a past gravitational encounter, a cosmic crime scene where we must work backwards from the motion of the survivors to deduce what happened. These outstanding questions are not dead ends. They are the most exciting part of the story, the fact that our own galactic backyard, the best-studied core in the entire universe, still holds such profound secrets is a testament to the breathtaking complexity of nature. Every mystery is a potential doorway. Solving the missing pulsar problem could revolutionize our understanding of stellar death. Pinpointing the origin of the Fermi bubbles could reveal the diet of a sleeping giant. Decoding the chaotic orbits could unlock the history of galactic violence. The core's unknowns are its greatest gift to future discovery. They ensure that the next generation of telescopes, from the Gravitational Wave Observatory (LIS) to the immensely powerful Vera C. Rubin Observatory, will have a clear mission, a list of cosmic riddles written in the heart of our own galaxy. In the end, the core's most important lesson may be this: that true understanding is not about having all the answers, but about knowing which questions to ask next. The search for answers does not belong only to those with access to giant telescopes. Some of the most important discoveries about the galactic center are now being made by people just like you, sitting at home with a computer and an internet connection. This is the world of citizen science, a global movement where public data from legendary observatories becomes a playground for curious minds. Imagine the vast archives of the Hubble Space Telescope, the Spitzer Space Telescope, or the Chandra X-ray Observatory. These machines have collected petabytes of information, far more than any single team of professional astronomers could ever analyze in a lifetime. That is where the public steps in. Projects like the Milky Way project invite volunteers to scan through stunning infrared images from Spitzer, tracing the delicate filaments and bubbles sculpted by newborn stars in the central molecular zone. By simply drawing shapes on their screens, volunteers help create the most detailed maps yet of our galaxy's chaotic star-forming factories, identifying structures that computer algorithms might miss. Another project might focus on the flickering heart itself, using data from Chandra to monitor the X-ray glow around Sagittarius, a star. A volunteer might be the first to notice a subtle, new brightening, a potential clue that the black hole is beginning to snack on a passing cloud of gas. This is not busy work, it is genuine frontline research. The human eye and brain are exceptional at pattern recognition, at spotting the unusual in a sea of normal. A citizen scientist in London or Tokyo might flag a star that changes brightness in a strange way, leading professionals to investigate a new type of variable star, or even a previously unknown microquasar near the galactic center. This crowd-sourced analysis accelerates discovery at an incredible pace, turning millions of hours of human curiosity into a powerful scientific instrument. But the impact goes far beyond processing power. By inviting everyone to participate, this research builds a profound bridge. It transforms the galactic core from a distant, abstract concept studied by experts into a shared landscape that we are all helping to explore and map together. When you spend an hour classifying dust clouds, you are not just completing a task, you are learning to see the galaxy's anatomy, to understand its rhythms. You become part of the story. This democratization of discovery is perhaps the most beautiful key of all. It reinforces that the quest to understand our place in the cosmos is not reserved for a select few, but is a fundamental collective human endeavor. The data is public, the tools are free, and the invitation is open. The next critical observation, the next piece of the puzzle that unlocks the secret of the galactic heart, could come from anyone, anywhere who chooses to look. The same technology that peers into the heart of our galaxy also saves lives. To see through the dust shrouding Sagittarius, a star, scientists could not rely on ordinary cameras. They had to invent entirely new ways of seeing. This required pushing the boundaries of infrared sensor technology, creating detectors of unprecedented sensitivity. These sensors, designed to catch the faintest whispers of heat from distant stars, have found a powerful second life in medical imaging. The precise, low-light detection principles developed for astronomy are now embedded in devices that help doctors detect cancers earlier, guide minimally invasive surgeries, and monitor vital signs with incredible accuracy. The quest to map the galactic core literally helps map the human body, turning cosmic curiosity into a powerful tool for health. Deciphering the blurry radio whispers of a black hole demanded another leap, the creation of the Event Horizon Telescope. This was not a single instrument, but a planet-spanning network of observatories working in perfect harmony. The technical challenge was staggering. It required synchronizing data from telescopes across continents and oceans with atomic clock precision. The algorithms developed to combine these signals, a process known as very long baseline interferometry, are masterpieces of computational problem solving. They do not just stitch images together, they find clarity in chaos, extracting a coherent picture from a sea of noise. This same sophisticated signal processing now enhances satellite communications, improves the resolution of Earth-observing systems that track climate change, and even refines the search algorithms that power internet services. The code written to see a black hole now helps us see our own world more clearly. Perhaps the most profound spin-off lies in the sheer volume of information. A single observation from a global telescope network or a space-based infrared observatory generates a flood of data, a digital universe that must be stored, sorted, and understood. The need to manage this deluge has driven breakthroughs in data compression, cloud computing architecture, and machine learning. Astronomers, facing a problem of cosmic scale, helped pioneer the techniques of big data analytics. These are the very tools that now allow meteorologists to model complex storm systems, enable financial institutions to secure global transactions, and help researchers track the spread of illnesses across populations. The computational engine built to simulate the accretion disk of Sagittarius, a star, is the same engine that can model the flow of a pandemic or optimize a national power grid. This chain of innovation reveals a beautiful and often overlooked truth. The drive to answer our most profound questions about the universe is not a diversion from practical progress. It is one of its most powerful engines. The extreme challenges posed by fundamental science, like observing an invisible object 26,000 light-years away, force engineers and programmers to think in ways they otherwise never would. They must solve problems that have no existing solution, building tools that push the absolute limits of the possible. These tools, born from pure curiosity, then filter down into our everyday world, transforming medicine, connecting global communities, and protecting our environment. The galactic core is more than a cosmic mystery. It is a crucible for human ingenuity. Every image of that dark heart, every map of its swirling stars, is a testament not just to what we have learned about the cosmos, but to what we have learned to build for ourselves. The investment in understanding a distant black hole pays a continuous dividend here on Earth, proving that when we reach for the stars, we also lift up our own world. The raw data from our telescopes arrives not as a picture, but as a language of numbers, a spectral signature, a map of radio wave intensities. To translate this alien information into something the human mind can grasp, we rely on a unique partnership between science and art. This collaboration is far more than decoration. It is a fundamental act of translation, turning the unseeable heart of our galaxy into a form that speaks directly to our senses and our emotions. When the Event Horizon Telescope team first processed the signals that would become the image of Sagittarius, a star, the initial result was not a crisp orange ring. It was a complex, noisy dataset that required sophisticated algorithms to reconstruct. The scientists worked alongside visual artists and data visualization experts to create a representation that was both scientifically accurate and intuitively understandable. They chose colors not arbitrarily, but to represent specific physical properties like the intensity of radio waves or the direction of magnetic fields. The final, now iconic image of a dark shadow encircled by a fiery ring is a masterpiece of this synthesis. It is not a photograph in the traditional sense, but a meticulous visualization built from petabytes of real data, a portrait of gravity itself made visible. This process extends far beyond a single image. To convey the frantic motion of stars around the black hole, animators take the precise orbital data tracked over decades and build dynamic, three-dimensional models. We can watch a star like S2 complete its 16-year loop in seconds, its path warping due to relativistic effects, a dance choreographed by equations of gravity and rendered into a visceral experience. These visualizations allow us to step into the core, to navigate through the dense nuclear star cluster, and to witness the scale of structures like the Fermi bubbles stretching far above the galactic plane. They make the abstract concrete, transforming light curves and velocity maps into a soaring journey through a cosmic metropolis. The artists act as essential guides, using composition, color, and movement to highlight what matters most, to tell the story hidden within the spreadsheets. A simple graph of a star's velocity over time is compelling to an astronomer, but a swirling animation of that star whipping around a dark vortex ignites wonder in anyone who sees it. This artistic interpretation bridges a profound gap. It connects the analytical power of science with the emotional power of human curiosity. A beautifully rendered visualization does not simplify the truth, it illuminates it, providing a gateway for the public to engage with discoveries that might otherwise remain locked behind technical jargon. When we look at these creations, we are not just seeing an artist's impression, we are seeing data-given form, the invisible architecture of our galaxy revealed through creative synthesis. The core's terrifying beauty and elegant violence become accessible, fostering a sense of connection and awe that pure data alone could never achieve. In this way, art becomes a vital key itself, unlocking public imagination and ensuring that the story of our galactic heart and its universal significance resonates far beyond the walls of any observatory. Our galaxy's heart has always been a blank screen for our deepest fears and boldest dreams. For generations of storytellers, that mysterious concentration of light in Sagittarius represented the ultimate destination, a place where the rules of reality could be bent or broken. Early science fiction often imagined it as a literal world, a colossal planet or a stable cosmic structure bathed in perpetual light, the throne of ancient empires or the home of godlike beings. These stories were pure fantasy, but they captured a fundamental truth, the human instinct to journey toward the center, to seek answers at the source. The science was absent, but the yearning was perfectly real. Then, as astronomy began to pierce the dust, the fiction evolved. The discovery of intense radio waves and the theorized black hole transformed the narrative landscape. The stable planet vanished, replaced by a terrifying and magnificent vortex. Arthur C. Clarke's 2001, A Space Odyssey, with its cryptic monoliths and stargate, hinted at a transcendent intelligence lurking near Jupiter, but the sequel, 2010, pointed directly toward the galactic core as a nursery for new suns and a realm of transformation. This shift mirrored science's own dawning realization that the center was not a place, but a process, an engine of creation and destruction. Modern science fiction now wrestles with the actual physics emerging from observatories. Films like Interstellar depict the supermassive black hole Gargantua not as a simple pit, but as a complex, luminous accretion disk, its gravitational lensing and time dilation portrayed with advice from a real astrophysicist. Video games build entire adventures around navigating the relativistic distortions and lethal radiation of a galactic core, forcing players to contend with the same extreme environmental challenges that scientists model in their simulations. The fantasy of a solid world has been replaced by the awe-inspiring and far more interesting reality of a space-time maelstrom. This evolution from fantasy to informed speculation creates a powerful feedback loop. Each new scientific revelation, like the image of Sagittarius, a star, or the discovery of the Fermi bubbles, provides fresh, raw material for storytellers. A documentary about stellar orbits inspires a novelist to write about a civilization living on a world whipping around a black hole, where the sky is a dizzying swirl of distorted stars. Conversely, a gripping film that treats time dilation not as magic but as a narrative constraint sends audiences searching for explanations, driving public curiosity and engagement with real science. The core serves as the perfect narrative device because it is the ultimate frontier within our own galaxy. It is a place of last voyages and first contact, of confronting the infinite and the infinitesimal. When a fictional starship ventures there, it mirrors our own scientific quest, a journey into the unknown driven by curiosity and the hope of revelation. Fiction follows the frontier of fact, and in doing so, it prepares our imagination for the truths we are still uncovering. The stories we tell about the galactic center are a cultural heartbeat, measuring how deeply our scientific understanding has penetrated the collective mind, transforming awe from superstition into a guided wonder. This global portrait of our galaxy's heart is being painted by a chorus of voices from every continent. The monumental task of decoding the core demands more than advanced technology. It requires a new kind of human cooperation. No single nation, no solitary telescope, possesses all the pieces of this cosmic puzzle. The landmark achievements we have witnessed, from the first image of a black hole's shadow to the precise map of 1 billion stars, are triumphs of international partnership. Consider the Event Horizon Telescope. It is not a physical instrument in one location, but a synchronized network of radio observatories spanning the globe from the high deserts of Chile and the peaks of Hawaii to the frigid plains of Antarctica and the mountains of Spain. To capture the faint radio whisper of Sagittarius, a star, these far-flung dishes must act as one single planet-sized eye. This requires an unprecedented level of coordination, with teams of scientists and engineers aligning their schedules down to the nanosecond, sharing petabytes of data, and merging their cultural and technical expertise to solve problems that have never been encountered before. Similarly, the European Space Agency's Gaia mission, which is revolutionizing our understanding of the Milky Way's structure and history by pinpointing the positions and motions of over 1 billion stars, involves hundreds of scientists and software engineers from across Europe and beyond, all contributing to a shared data treasury that is freely available to the world. These are not merely scientific projects, they are diplomatic and logistical marvels. They require nations to pool funding, to negotiate access to sovereign airspace for data links, and to build trust that the fruits of this shared labor will benefit all of humanity. The study of our galactic core has, perhaps unexpectedly, become a powerful model for peaceful, collaborative big science. In a world often divided, it represents a frontier where competition gives way to a collective need to know. Engineers in Japan work alongside theorists in Germany to calibrate an instrument in Chile, all to understand a gravitational mystery 26,000 light-years away. This global endeavor transforms the quest from a purely intellectual pursuit into a shared human story. It proves that our most ambitious questions can only be answered by looking outward together. The key to understanding all galaxies is not being forged in a single laboratory, but in the interconnected web of human curiosity that now spans the Earth, uniting us in a common project of cosmic discovery that belongs to everyone. This shared journey of discovery carries a quiet but profound weight, as we stand on the verge of not just understanding but simulating the very hearts of galaxies. A new kind of question emerges, one not of physics but of principle. What is our responsibility with this kind of knowledge? The power to model cosmic evolution, to predict the life cycles of stars and black holes, is a monumental achievement. Yet it invites us to consider a future where such understanding might one day allow us to contemplate influencing phenomena on a truly galactic scale, a thought that moves us from observers to potential participants in the cosmic story. This is not a call to immediate action, but a necessary moment of reflection. With such profound insight comes a duty to ask how we will use it. The primary ethical imperative is clear: to ensure this knowledge remains a tool for enlightenment and benefit, not for division or harm. The maps we make of the galactic core, the algorithms we write to decode its light, should be open treasures for all of humanity, fostering global collaboration and inspiring generations to look up with wonder, not down with fear. This extends to protecting the very window through which we see. The growing blanket of artificial light that shrouds our night skies is more than an inconvenience. It is a slow closing of a cosmic frontier. Preserving dark skies for observation is an act of stewardship, safeguarding not just data for scientists, but a source of inspiration and humility for every person who has ever gazed at the Milky Way's faint band. It is a commitment to keeping the universe accessible, reminding us that we are part of something vastly larger than our own creations. Ultimately, exploring the core is as much a philosophical journey as a technical one. Unraveling the mysteries of a supermassive black hole does not separate us from the cosmos. It deepens our connection to it. This knowledge compels us to reflect on our fragile place within an ancient and violent universe, highlighting the preciousness of our stable planet and the thin thread of conditions that allow us to exist and to ask these questions. The greatest responsibility that comes with cosmic insight may be this: to steward our own world with the same wisdom and care we are learning to apply to the galaxies. Understanding the universe is not an escape from Earth, but a deeper way of belonging to it, a reminder that with great vision comes the duty to see clearly, not just across the light years, but right here at home. The quiet heart of our galaxy is about to be seen with a clarity that will rewrite every textbook. A new generation of cosmic observatories, both in space and on remote mountaintops, is poised to turn the key on the core's deepest secrets, ushering in a golden age of discovery. First, the James Webb Space Telescope, with its unprecedented infrared vision, is already piercing the thickest veils of dust. It is not just seeing stars, it is reading their chemical fingerprints in exquisite detail, revealing the precise composition of the gas swirling toward the black hole, and identifying the very youngest stellar objects born in the hostile environment of the central molecular zone. This will tell us definitively how stars can form under such extreme gravitational stress. Joining Webb will be the Nancy Grace Roman Space Telescope, a surveyor on a colossal scale. While Webb zooms in on specific details, Roman will pull back to capture the entire galactic center in a single, sweeping gaze, monitoring millions of stars at once. Its mission is to map the grand choreography, detecting the subtle, telltale wobbles in starlight that betray the gravitational tug of hidden objects, from intermediate mass black holes to vast dark clouds. This wide-field census will finally answer whether that predicted swarm of middleweight black holes truly exists around Sagittarius, a star. On Earth, in the pristine skies of Chile's Atacama Desert, the extremely large telescope is rising. With a primary mirror nearly 40 meters across, this ground-based giant will collect more light than all of history's major optical telescopes combined. Its power will be staggering, allowing it to directly image the motions of individual stars much fainter and closer to the black hole than ever before. It will track their relativistic orbits with pinpoint precision, testing Einstein's theories in even more extreme regimes and potentially capturing the moment a star is gravitationally lensed, its light stretched and bent by the black hole's space-time warp. Perhaps most thrillingly, the global collaboration behind the Event Horizon Telescope is refining its planetary scale network. The goal is no longer just a single, iconic image of the black hole's shadow, but a high-definition movie. By adding new telescopes and employing more advanced algorithms, scientists aim to capture the dynamic flicker and flow of material in the immediate vicinity of the event horizon, watching the black hole's feeding habits in real time and seeing how its powerful magnetic fields structure the infalling chaos. The combined data from these missions will be a transformative flood. We will move from snapshots to a continuous, multi-wavelength film of the galactic core in action. We will have a three-dimensional map of stellar motions, a census of hidden masses, and a dynamic portrait of accretion physics. This is not merely more information, it is a new way of seeing. The coming decade promises to turn the key we have been crafting for so long, unlocking the core's final mysteries and, in doing so, providing the definitive blueprint for the heart of every spiral galaxy in the cosmos. The ultimate challenge now is not collecting more pieces, but learning how they all fit together. We have an overwhelming wealth of information, a dizzying array of clues from different wavelengths and messengers, each telling a part of the story. The frantic orbits of stars speak the language of gravity. The chemical fingerprints in stellar atmospheres whisper tales of ancient star formation. The faint gamma-ray glow maps a hidden storm of particles. The silent hum we hope to hear would be the vibration of spacetime itself. These are not separate stories, they are different chapters of a single epic narrative. The grand and profoundly difficult task facing astrophysics today is to synthesize all of this disparate data into one unified model of the Milky Way's core. It is a challenge of staggering complexity, like trying to assemble a million-piece jigsaw puzzle without ever having seen the picture on the box. Each new observation is another piece handed to us, but the final image, the complete theory of how a galactic nucleus truly functions, is still emerging from the fog. The goal is not just a static description, but a living, predictive simulation. A successful unified theory would be a digital twin of our galactic heart, a virtual core so accurate that if you input the conditions from 6 million years ago, it would naturally produce the Fermi bubbles we see today. If you simulate the passage of a giant gas cloud, it would correctly predict whether the cloud forms new stars, gets shredded into a glowing stream, or simply adds to the black hole's quiet accretion disk. This model would seamlessly connect the large-scale bar-driven inflow of gas to the microphysics of magnetic fields around the event horizon. It would explain why some stars are on wildly eccentric orbits while others trace calm circles, and it would account for the bizarre population of G objects as a natural consequence of stellar dynamics in such a crowded space. Every strange observation, from the missing pulsars to the faint X-ray flares, would find its logical place within the framework. Building this is a monumental exercise in computational and theoretical physics, requiring teams to bridge disciplines that have traditionally worked in isolation. The stellar dynamicist who models orbits must now constantly compare notes with the plasma physicist simulating magnetic turbulence, and both must ensure their work aligns with the chemist who reads the elemental abundances in starlight. Achieving this synthesis for our own galactic center would be the final and most powerful master key. It would represent a complete, validated instruction manual for a standard galactic nucleus. Once we possess a theory that accurately explains everything we see here, from the quiet present to the violent past, we gain something extraordinary, a universal framework. We could then apply that framework, with adjustments for mass, size, and cosmic era, to the core of any galaxy we observe. The brilliant, unresolved point of light at the heart of the Andromeda galaxy would no longer be a mystery, but a set of initial conditions we could plug into our model. The furious quasar blazing in a distant young galaxy would be recognizable as our own Sagittarius, a star in a different, more energetic phase of the same life cycle. This theory would allow us to read the history and predict the future of galaxies across the universe, simply by analyzing the integrated light from their centers. It transforms the core from a subject of study into the Rosetta Stone for galactic evolution itself. The synthesis of all we have learned about our own quiet heart is ultimately the quest for a grammar book to understand the stories written in the hearts of 100 billion other islands in the dark. The furious physics of our galactic heart does not just map the present, it echoes the deep past. To understand the universe in its fiery infancy, we do not need a hypothetical time machine, we have a real one operating right now in the constellation Sagittarius. The core of the Milky Way, with its extreme radiation, frantic star birth, and overwhelming gravity, is a rare local relic, a pocket of the ancient cosmos preserved in our modern galactic neighborhood. This is because the early universe was a fundamentally different place. Billions of years ago, space was smaller, denser, and far more chaotic. Galaxies were just assembling themselves, often through violent collisions, and their gas reservoirs were pure, uncontaminated by the heavy elements forged in generations of stars. In this primordial environment, conditions were not gentle. Intense ultraviolet radiation from the first massive stars flooded space. Gravity ran wild in dense knots of matter, and the supermassive black holes that were beginning to form at the centers of protogalaxies were likely far more active and dominant than they are today. We see a scaled-down, modern reflection of all this in our own galactic core. The central molecular zone, for instance, is not a serene stellar nursery. It is a pressure cooker where stars form in frantic, massive clusters, not in gentle isolation. This frenzy of collective birth, dominated by short-lived stellar giants, is precisely what astronomers believe was the standard mode of star formation in the early universe. Those first stars, known as population 3 stars, are thought to have been monsters, hundreds of times the mass of our Sun, living fast and dying in spectacular supernova that seeded the cosmos with the first heavy elements. We cannot see those original stars directly. Their light is too faint and redshifted after traveling for over 13 billion years. But by studying the massive, rapidly forming stars in our own core, we are essentially reading a nearby, contemporary translation of that ancient story. The physical processes of collapse, the role of turbulence versus gravity, the way radiation from newborn stars affects the surrounding gas, these are universal laws. By decoding them in our own backyard, we calibrate our models of cosmic dawn. Similarly, the feeding habits of our supermassive black hole, Sagittarius a star, offer clues to a more ravenous era. While it is quiet now, its occasional flares and the fossil evidence of the Fermi bubbles show it can awaken. In the early universe, the seeds of supermassive black holes found themselves in a target-rich environment, surrounded by vast amounts of pristine gas. They likely fed in almost continuous outbursts, shining as brilliant quasars that could outshine their entire host galaxies. These quasars were not just beacons, they were powerful engines that shaped the evolution of the first galaxies through their intense radiation and energetic jets. By studying the detailed mechanics of accretion and feedback around our own dormant black hole, by measuring how it interacts with nearby gas clouds and influences star formation, we are learning the basic operating principles of those primordial monsters. Our core provides the instruction manual for the central engine of a young galaxy. Furthermore, the very structure of the early universe favored environments like our core. The first galaxies were much smaller and denser than the majestic spirals we see today. In a sense, the entire galaxy might have resembled just the core region of a modern giant. The black hole's influence would have been proportionally much greater, its feedback effects more immediate and dramatic. Studying the intricate gravitational dance and energy flow within our few hundred light-year-wide core is therefore like studying a miniature, slowed-down version of an entire infant galaxy. We are witnessing the dominant physics that once governed cosmic structures on a much larger scale. This transforms the galactic center from a mere curiosity into a vital archaeological site. Every frantic orbit, every burst of star formation in the central molecular zone, every wisp of gas spiraling inward is a data point in a grand experiment about origins. We are not looking back in time with a telescope. We are using a local, extreme environment as a physical analog. It is the difference between trying to imagine a dinosaur from a fossil and observing a large, powerful reptile alive today to understand the principles of paleobiology. Our galactic heart is that living proxy, a cosmic window that lets us watch the violent, creative processes that built the universe from the inside out, offering a tangible glimpse into the tumultuous dawn of everything. This realization quietly reshapes our place in the cosmos. For centuries, the human story was one of seeking a literal center, a fixed point around which everything else revolved. We placed Earth, then our Sun, at the heart of creation. Each discovery moved us further into the cosmic suburbs, a lesson in geographic humility. Yet the galactic core offers a different kind of lesson altogether. We are not at the center of the universe, but we may inhabit the most central vantage point for understanding it. Our position is not one of privilege, but of perfect perspective. From our quiet spiral arm, we possess a front row seat to a phenomenon that is both profoundly unique in its detail and utterly universal in its principles. The violent, beautiful processes churning in Sagittarius, a star's neighborhood, are not just local events. They are the standard operating system for the heart of a spiral galaxy. This transforms our cosmic address from a humble outpost into a singular observatory. We are like naturalists who, by a stroke of immense fortune, live right beside the only fully accessible rainforest of its kind. We can walk among its trees, catalog its creatures, and feel its climate, while the rest of the world possesses only distant, blurry photographs of similar jungles. Our knowledge of this one ecosystem becomes the key to understanding all of them. This is a new kind of centrality, one built not on location but on insight. The core grants us a Rosetta Stone written in the language of gravity, light, and time. By learning to read it here, we gain the ability to translate the faint signals from the hearts of galaxies so distant their light began its journey before Earth formed. That connection is profound. It means the same forces that govern the frantic dance of stars around our own quiet giant also choreograph the brilliant quasars that illuminated the early universe. The physics that carved our Fermi bubbles sculpts the colossal radio lobes of galaxies millions of light-years away. We are not separate from the grand tapestry. We are woven into it by a common thread of physical law. Our backyard laboratory reveals a shared cosmic heritage. This fosters a deep, intellectual kinship with the universe. It replaces the old loneliness of a planet adrift in emptiness with a resonant sense of belonging to a coherent, comprehensible whole. The chaos at our galaxy's heart is not an alien spectacle. It is a familiar blueprint. We find our significance not in being at the center of the map, but in holding the key to reading every map there is. Our journey from the center of creation to a minor planet orbiting an average star has led us, paradoxically, to the most meaningful center of all, the center of understanding. So here is a question for you, a choice that gets to the very heart of our journey. What do you believe is the single most important reason our galaxy's core holds the master key to understanding all others? Is it A, our incredible front row seat, the unique, detailed view we have from within the Milky Way that no external observer could ever match? Or is it B, the profound calm of Sagittarius, a star, its quiet presence offering the perfect baseline to understand the violent outbursts of quasars in distant galaxies? Perhaps you think it is C, the extreme, chaotic conditions for star formation in the central molecular zone, a living fossil of the universe's fiery youth. Each answer is compelling, and each reveals a different facet of this cosmic detective story. Your perspective matters. Cast your vote with a letter in the comments below, and let's see what the community thinks is the core's most vital clue. This is more than a quiz. It is a way to step into the role of an astronomer weighing the evidence. If you chose our front row seat, you are highlighting the irreplaceable gift of our location. It is the reason we can track individual stars, map magnetic filaments, and hope to catch a stellar demolition in real time. This intimate access turns abstract theory into observable fact. If you selected the calm of our black hole, you are focusing on the power of contrast. The quiet of Sagittarius, a star, defines normalcy, letting us recognize the extraordinary violence of an active galactic nucleus as a dramatic but temporary departure from a long, peaceful chapter. And if you pick the extreme star formation, you are looking back in time. You see the core as a local portal to the early universe, where the frantic, cluster-based birth of massive stars was the rule, not the exception. Decoding that process here is our best hope for understanding cosmic dawn. There is no single wrong answer because these reasons are not isolated. They are interconnected threads in the same grand tapestry. Our front row seat allows us to study the calm and the chaos in exquisite detail. That detailed study of calm gives context to the violence we see elsewhere. And the chaos itself mirrors the primordial past. They build upon each other layer by layer to form a complete picture. By sharing your choice, you are not just answering a question, you are engaging with the very method of science, prioritizing one piece of a magnificent puzzle. It is a small act of participation in a story that belongs to all of us. So tell me which key feels most powerful in your hand. The comments are open, and I am genuinely curious to see where our collective curiosity points. The heart of our galaxy speaks a universal language. This journey has shown us that the chaos at the core is not a random spectacle, but a carefully orchestrated process, a prototype for the hearts of countless other spiral galaxies. The frantic orbits of stars, the quiet anchor of Sagittarius, a star, and the ghostly echo of the Fermi bubbles are not isolated features. They are interconnected chapters in a single cosmic instruction manual. Each discovery here, from the strange G objects to the frenzied star formation in the central molecular zone, provides a high-resolution data point, a natural experiment that lets us test our theories against reality with an intimacy impossible anywhere else in the universe. This transforms our galactic center from a subject of study into the ultimate reference manual. It is the detailed blueprint against which we can now compare the faint, blurred signals from the cores of galaxies millions of light-years away. The violent outburst of a distant quasar, the faint radio whisper from an elliptical galaxy's heart, the strange motions of gas in a merging system, all become legible because we have learned the alphabet of forces here in our own cosmic backyard. The key to understanding the grand architecture of the universe was not hidden in some distant, unreachable realm. It has been orbiting silently in the constellation Sagittarius all along, waiting for us to learn how to see. Our quest is far from over. With every new telescope, every citizen scientist's classification, and every advanced simulation, we add another sentence to this universal translation. As we continue to observe, to question, and to wonder, remember this: each breakthrough at the center of our own galaxy does not just illuminate a single point of light. It turns on a lamp that helps us see the entire cosmic tapestry, revealing the shared story written in the hearts of 100 billion island universes. Thank you for exploring this frontier of understanding. If this journey into the universal language of galaxies sparked your curiosity, consider subscribing for more deep dives into the universe's greatest mysteries. We would love to hear which piece of the puzzle you find most compelling, so share your thoughts on the galactic key in the